So, welcome to the short video about unique factorization and standard factored form. So, recall the unique factorization theorem. It applies to an integer n as long as n is greater than or equal to 2. And what it says about n is that n can have a unique factorization as a product of powers of primes. In other words, n is equal to p sub 1 raised to the e sub 1 times p sub 2 to the e sub 2 times times p sub k raised to the e sub k, where each p sub I is prime, p sub I is less than p sub j whenever I is less than j, which simply means these are written in order by size, starting with the smallest and ending with the largest prime factor. And each exponent, e sub I, is a positive integer. We do not want negative powers, and we don't want to allow zero because we don't want superfluous primes to appear as if they are factors when in fact they are not. Also recall the perfect square fact. If x is greater than or equal to 4 and x is a perfect square, we learned something about the factored form of x. That means x is equal to n squared for an n that's at least as big as 2, of course, if x is at least as large as 4. So n has a prime factored form. So we write n in its prime factored form. And then we raise, oops, it should be a k. Then we raise that to the second power to look at x. So x is n squared. So that exponent of 2 that is here, because we're looking at n squared, gets distributed. And we use laws of exponents to realize that, hey, x looks like p1 raised to the 2e1 times p2 raised to the 2e2 times times p sub k raised to the 2e sub k. That means each one of these exponents is divisible by 2. So that was the fact that we looked at last week. Each exponent in the standard factored form, that's what we call this, of x is divisible by 2. And you can think about this and you can imagine, hey, if x is a perfect cube, then x equals n cubed, and this exponent of 2 is instead of 3. And so if x is a perfect cube, then each exponent in the standard factored form of x would have a factor of 3. In other words, would be divisible by 3. And you can play this game for any power. You know, if x equals n to the 4th, then each one of these primes would have an exponent that's divisible by 4, and so on and so forth. So the last problem on the special homework talks about finding the smallest positive integer k to make a number x or n a perfect square or a perfect cube. So let's look at one of those. Example 1. Find the smallest positive integer k. So, I mean, there are lots of k's that would work, but we want to find the smallest one that's, of course, positive. Integer k that will make, let's call it n, say n equal 2 cubed times 3 to the 8th times 5 squared times, let's just add a few more in here, say 7 to the 7th, why not, times, say, 11 to the 1 times k, a perfect square. and verify n is a perfect square by factoring it as a perfect square. And then we could play the game where we try to find the smallest positive integer k that would make n a perfect cube. And we can verify that n is a perfect cube by factoring it as such. So the game is simply to build k in such a way that it corrects any of the exponents that need to be corrected to achieve either goal. So let's start with the goal of making n a perfect square. So if we want to make n a perfect square, we look at the factors of n and we ask ourselves, okay, could this factor 2 cubed be correct if we want n to be a perfect square, or is it going to need to be adjusted? The same thing for the prime factor 3. It's being raised to the 8th. Is that an appropriate exponent for n to be a perfect square? Same thing with 5 squared. Is this 2 an appropriate exponent if we want n to be a perfect square? And so on and so forth. Well, let's just think about what we're going to do to correct any exponents that aren't satisfying the fact that each exponent in the standard factored form of x, when it's a perfect square, is divisible by 2. They all have to be divisible by 2. Well, let's look at the first factor, 2 cubed. This 3 is not divisible by 2. So if we add 2 as a factor of k, then that will correct this 3 and make it a 4. When we rearrange these and collect the 2's all together, it'll be 2 to the 4th, and that will be a decent factor for a perfect square, because a 4, of course, is divisible by 2. Let's move on to the next factor, 3 to the 8th. Well, this exponent is 8, and that is divisible by 2, and it doesn't need any, additions or subtractions. It's divisible by 2 as it stands, and we can move on. 5 squared is okay because 2 is divisible by 2. 7 to the 7th, however, needs an adjustment because 7 is not divisible by 2. So if we add a factor of 7 to the 1, then this will become 7 to the 8th, and of course 8 is divisible by 2, and that will correct the 7 to the 7 factor. 11 to the 1, of course, won't work because 1 is not divisible by 2, but if we add the factor of 11 here to the k that we're building, see we're building k here, then that will correct 11 to the 1, and it'll be 11 to the 1 times 11 to the 1, or 11 squared. So now let's just see what's happened. We've got n is equal to 2 cubed times this 2 times 3 to the 8th. Of course, you don't have to show this intermediate step if you don't need to. Times 5 squared times 7 to the 7th times 7 to the 1, just putting that close to that, times 11, which is equal to 2 to the 4th times 3 to the 8th times 5 squared times 7 to the 8th times 11 squared. And now that's a perfect square. And we verify that by simply splitting those exponents in half using the laws of exponents. And we can see what the square root of n is. It's this integer, 2 squared times 3 to the 4th times 5 times 7 to the 4th times 11. So that's the way we build the k to make n a perfect square. If we want to make n a perfect cube, we understand that every exponent in the standard factored form of n needs to be divisible by 3. So as we build the k to correct any exponents that are not divisible by 3, we simply add enough copies of that prime base needed in order to build up enough to have an exponent that's divisible by 3. So 2 cubed, well, 3 is divisible by 3, so it's okay. 3 to the 8th, however, needs an adjustment because 8 is not divisible by 3, but 9 is. So if we add one factor of 3, then 3 to the 8th times 3 to the 1 will become 3 to the 9th, and 9 is divisible by 3. 5 squared, well, that needs an adjustment because 2 is not divisible by 3, but 3 is. So if we add one copy of 5, that will correct this exponent and make it 5 cubed. 7 to the 7th, well, that needs work because 7, this exponent, is not divisible by 3, but neither is 8, but 9 is, so we need to add a factor of 7 squared to correct the 7 to the 7th and make it 7 to the 9th. 9 is divisible by 3. Same idea here. This is 11 to the 1. To correct that and get an exponent that's divisible by 3, we need to add 2 copies of 11. And we can verify now that this n is a perfect cube because we've got 2 cubed times 3 to the 9th. I'll just do this in one step. Times 5 cubed times 7 to the 9th times 11 cubed. And that is a perfect cube. Because we can pull out the 3 and we've got 2 times 3 cubed times 5 times 7 cubed times 11. So now we've written n as a perfect cube. So you can do later one more on your own time. Find the smallest positive k. Of course, it's an integer. To make n equal to x to the 4th for some integer x. In other words, make n a perfect quartic. We call that a perfect quartic. Or you could play the game and make n a perfect quintic. In other words, n would equal x to the 5th for some integer x. I hope this helps you with your special homework, and thanks for stopping in to our short video.